Alright, hi everybody, welcome back. So we are going to finish up chapter 9 today. So we've been talking a lot about hypothesis testing and being able to run a hypothesis test using either a mean or a proportion, right? So we've been looking at mu versus p, x bar versus p hat. So what we're going to start looking at today is some additional hypothesis testing. We're going to look at another methodology for running hypothesis tests, and then we're just going to look at several examples dealing with this concept. So to start us off, they just kind of highlight for us the steps in hypothesis testing. So there's 3 phases that we go through, and that is to make a statement. So that's, what is the general assumption, the null hypothesis being kind of what's generally assumed to be true already. And then the alternative hypothesis is what we are trying to show is actually true. So you make that statement, you collect your evidence, right, or your data to test that statement, and then you analyze the data. So all 3 of these very important steps in being able to successfully carry out a hypothesis test. So one of the things that we're going to talk about first is the concept of something being statistically significant or being what we call unusual or rare. So for this example, in the California lottery, the odds of winning the first prize Super Lotto jackpot are 1 in 41,416,353, and the odds of winning the Mega Millions is 1 in 302,575,350. Why would we consider winning either of these events unusual? So you might be able to just look at that and say, well, the odds of winning are extremely, extremely low, right? But we can actually put a number to that. So if we look at the probability of winning the Super Lotto, okay, that's going to be, you have a 1, assuming you buy 1 ticket, that would be 1 out of 41,416,353, which, if you write that as a decimal, is let's see, we're going to have 1, 2, 3, 4, 5, 6, 7 zeros, so 1, 2, 3, 4, 5, 6, 7 zeros, 2, 4. Okay, so your probability of winning is 0.00000024. So as a percentage, that's still a 0.000024% chance of winning. So significantly less than 1% chance of winning. And that's the Super Lotto. That's not even the Mega Millions. So the probability of winning the Mega Millions is going to be 1 out of that huge number, right? The 302, etc. So 575, 350. If you get a decimal approximation for that, you're going to get 0.0000000033. So that's point with 8 zeros, 33. So we're talking an even smaller probability of winning. So why would we consider these events to be unusual? Because the probabilities are extremely low. Probabilities are very low. Now, this doesn't necessarily mean the probability has to be that low for an event to be considered unusual. In fact, our threshold for an unusual event is usually around 5%. So an unusual event is what we would label it if it had less than a 5% chance of occurring. We would call that unusual. And of course, there's some wiggle room there. It's not a hard line 5%. but anything certainly less than 5%. And when you start getting more than 5%, then you start having a conversation about, well, it is possible, right? It's somewhat likely. It's not highly unusual that this event would occur. But 5% is generally our threshold. Okay? So when we look at observed results, and these are unlikely, under the assumption that the null hypothesis is true, we say that this result is statistically significant. So if we have our null hypothesis, right, and we say, okay, I'm assuming that this is just the way it is, we're going to assume that that's true. And then we run our test, and our observed results give us something that's very, very unlikely to occur. Okay, so again, null hypothesis means status quo, right? We're assuming that the normal is true. And then we get something that, if that normal thing was true, this would be extremely unusual to have this result, which tells us maybe that null hypothesis isn't true, right? Maybe our alternative is actually more accurate. Okay, and so when we have results that are highly unusual given the null hypothesis being true, we say that that is statistically significant. Okay? So when we find that results are statistically significant, we reject the null hypothesis. Okay? So if we get highly unusual result given that the null hypothesis is true, then we reject the null. We say, well, this must not have been correct to begin with. Okay? So now some more terminology here. The p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. Okay, so what this is saying, so a p-value is a probability. So it's going to be some area here, some area under this curve. So this is going to be our p-value. Okay, so this is the probability that this event would occur, or something more extreme than this event would occur, given the null hypothesis is true. If this value, the probability of this happening, is very, very small, that means it's highly unlikely, which means we would reject the null hypothesis. Okay? Whereas if the p-value was really large, that tells us that's pretty likely. It's pretty likely to occur, so we would not reject the null hypothesis. Okay? And generally, the test that we're going to be working with is we're comparing the p-value with alpha. Okay? That probability of making a type 1 error. If we say that the p-value is smaller than alpha, then we say that the result is statistically significant, and we reject the null. So if alpha, let me use a different color here. So if alpha was just ever so slightly larger than the p-value, then we would say that this is statistically significant because the p-value is highly unlikely or unusual. Okay. So here we have an example. So a normal distribution has a standard deviation of 1. We want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5. Draw a graph that shows the p-value. Okay, so here we have our mean of 12, our null hypothesis, and our alternative hypothesis. Okay, so we got in our sample, we had a sample mean of 12.5, and the p-value is 0.0013. So what that means is the probability of getting a value of 12.5 or higher is going to be 0.0013, which is very unlikely, right? That would be a 0.13% chance. So if we have our mean of 12, then our value of 12.5 is going to be somewhere up here. Right, and then our p-value, that's probably a bit smaller than that, but you get the idea. This is our p-value. Okay. So the p-value of 0.013. So let's interpret kind of what this statement is telling us. Okay, the fact that the p-value is so small. Okay, so this tells us, so if the mean is really 12, right, if the null hypothesis is true, we would only expect a sample mean of 12.5 or higher, 0.13% of the time. This is highly unlikely. So we say the result is statistically significant. And we reject the null hypothesis. Okay. So again, this statement down here, that's really a nice kind of summary, a good conclusive statement of what's happening here. So if the null hypothesis was true, if the mean was actually 12, this result of getting 12.5 would be very, very unlikely, which means that the mean being 12 was probably not the case to begin with, right? It's probably higher than that. So we would then reject the null hypothesis. Okay. All right, so decision and conclusion. So now it's talking about what kinds of conclusions can we draw based on these p-values. So oftentimes we will be comparing the p-value to alpha, right? So that's going to be our primary way of determining whether something is statistically significant or not, is comparing whether the p-value is less than alpha or not. Okay? So let's look at this example. So It's a Boy Genetics Labs claim their procedures improve the chances of a boy being born. The results for a test of a single population proportion are as follows. So the probability of getting a boy is 0.5, right, boy or girl. But they claim, their alternative hypothesis is that the probability of getting a boy with their procedure is higher than 0.5. You have a greater chance than 50% of getting a boy. And they're testing it at a 0.01 level of significance, so a 99% confidence. And we get that the p-value is 0.025. Okay, so the probability of getting these results with p being 0.5 would be about 2.5%. Right? That's the chances of that occurring. Now, if we compare the alpha value with the p-value, okay, so we have the alpha value is 0.01, so that's 1%, so that's somewhere in here, right? That's 0.01, that's alpha. And 0.025, so hopefully everybody sees that that's a larger number, right? It's actually over twice as big, it's 2.5 times. So that's going to be up here somewhere, and that's containing all of this area. So that's going to be 0.025. Oops. 0.025, so that's our p-value. Okay. So since our p-value is larger than our alpha value, that means that it's actually somewhat likely. Okay, so it's not entirely out of the realm of possibility that you could get this result, even if the probability was 0.5 to begin with. So even if the null hypothesis was still true, you could still get this result. So that's not boding well for their procedure. So this tells us, so since the p-value, the p-value is greater, the result is not statistically significant. So we do not reject the null. Okay. Now, when we're making our conclusions here, you have to be careful how we state this, because we're not disproving or proving anything. We're not saying, oh, well, their treatment has no effect, right? It's 50-50 and they're not going to change that. That's not what we're saying. We're just saying that there's not enough evidence from this study to make that conclusion. Okay, so the way that we always state this is not we proved it or we disproved it, because there is no proving here. We're just talking about, is there enough evidence? So in this case, we say there is not sufficient evidence to conclude that their procedures make the chances of getting a boy higher. Okay, so again, we're not concluding 100% certainty that it doesn't work, but we are saying there's just not enough evidence to say that it does. Okay, so maybe they do more studies, they get more results, and then we can reanalyze any new data that they get. Okay, so let's look at this next one. So the administrator at a local hospital states that on weekends, the average wait time for emergency room visits is 10 minutes. Based on discussions on the length of wait time to be seen in the ER over a weekend, an employee disputes the administrator's claim. The employee decides to test his hypothesis. Over the course of a few weekends, the employee records the wait time for 40 randomly selected patients. The average wait time for these 40 patients is 11 minutes, with a standard deviation of 3 minutes. Does the employee have enough evidence to support his claim that the average ER wait time exceeds 10 minutes? He tests at a 5% level of significance. And then if we do not reject the null hypothesis, then what is the employee's conclusion? Okay, so first let's state our hypotheses here. So the null hypothesis is what's already generally accepted. So we're going with what the administrator said, and that is that the mean wait time is 10 minutes. Okay, but this employee, his alternative hypothesis is that the mean wait time is greater than 10 minutes. Okay, so we have a few pieces of data here that we can work with. So let's see, he took some data himself, so here's our hypotheses, and he got a sample mean, right? He got it to be 11 minutes. The standard deviation he got was 3 minutes, and he's testing at the 5% level of significance, so alpha is 0.05. Okay, so we'll need those. Okay, so now what we're looking at, so here's, right, our assumed mean is 10, somewhere up here is 11, and this probability, that's our p-value. And we need to determine if the p-value is going to be greater than the alpha value of 0.05. If it is bigger than alpha, then we say it's not that unusual, it's still within kind of our regular range, so we don't reject the null. But if we see that it's less than alpha, then we would reject the null, because we'd say that that is very significant evidence. Okay? So what we're looking for here, so our p-value, oops, so our p-value, that's going to be the probability that x bar would be greater than or equal to 11. Okay, so let's go ahead and run this over to Desmos so that we can run this calculation. Okay, so we're using the normal distribution, okay, with a mean of 10 and a standard deviation of 3. Okay, so here's our curve up here, so it's pretty flat, and we're looking for the probability that our value is greater than 11. Okay, so you can see there's 11 right there, and we're looking at that area above that. So we get that this is approximately 0.3694. this is approximately 0.3694. Alright, so that tells us that if the null hypothesis was true, if the average wait time was in fact 10 minutes, then the probability of getting an 11-minute mean in his sample, the probability of that happening is about 37%, which is not unusual. So this is certainly significantly greater than 0.05, which was alpha, right? That's our alpha value. So what this tells us is we do not reject the null. Okay, so here we do not reject the null. Okay. So if the mean is 10 minutes, this sample mean of 11 minutes would be expected about 37% of the time, so not unusual. Thus, there is insufficient evidence. There is insufficient evidence to claim the wait time is, I should say, the mean wait time. The mean wait time is above 10 minutes. Okay, so again, that's not saying with 100% certainty that the mean wait time is not above 10 minutes, but it's saying given his particular data collection, his study, there is not sufficient evidence to make that conclusion. Okay. All right, so that gives us our result there. All right, so let's go ahead and move into section 9.5. So on the first page here, we're just looking at kind of a breakdown of all of our different ways of conducting hypothesis tests, and we're going to do several examples here. So, but our procedure is as follows. So first step, of course, is determine those null and alternative hypotheses. Okay, so and then we're going to determine what type of test we're doing. We select a level of significance. If it doesn't give us one, then assume that you're using 0.05 for the significance level. Okay. And then it'll be up to us to determine which approach we want to use. So they provide 3 here. We're going to mostly focus on the first 2, so that's the classical approach and the p-value approach. The confidence interval approach also works. They're all kind of hovering around the same idea, so they're not that different from each other. But we're going to focus mostly on these first 2, and we've been looking at means and proportions. Okay, so for the mean and proportion, we're going to get our test statistic. So the test statistic is just going to be that z-score, that t-score that corresponds to our value, okay, our x-bar, our p-hat, whatever that might be. And then we determine what we call the critical value. Okay, this critical value comes from whatever the alpha value is. Okay, and again, we'll see this in examples. We're going to then compare, different color, we're going to compare the critical value with the test statistic. Okay, if we find that our critical value is within the critical region, so when we say the critical region, we mean it's outside of that critical value. Okay, so if it's past our alpha z-score, then we can reject H0, because we say that that event is unusual, given the null hypothesis. Okay, and then for the p-value, right, we just kind of looked at this, but you find your p-value, that probability, and then you compare, so you compute the p-value and then compare the p-value with alpha. Okay, so and if it's smaller than alpha, we reject the null. If it's greater than alpha, we do not reject the null. Okay, And then same thing with the confidence interval. You can create a confidence interval and then just determine if your confidence interval contains the null hypothesis value or not. And that would give you that information. So if it does not contain the null hypothesis value, we reject the null hypothesis. Okay? And then, of course, the last step would be to make a conclusion. Okay? So not only do we say reject or do not reject, we need to answer in context. So we just need to make a statement about whether or not there's sufficient evidence here. Okay, so then we have our three types of tests, and that is two-tailed, left-tailed, and right-tailed. So we've seen all three of these before, and we will see examples with them as well right now. So, but these are our different types of tests that you can have, depending on whether a value is, our alternative hypothesis is just that they're not equal, or one is bigger than the other. Okay? So if you want to look at the calculator steps, that's up to you, but I'm going to be using Desmos throughout this. So, okay. So for the first example here, so I do need to make an amendment to this one. There is a missing piece of information that's going to come in right here after this first sentence. So it reads, so the mean throwing distance of a football for Marco, a high school freshman quarterback, is 40 yards. And then I need to add in one piece of information here. And this is with a standard deviation of 2 yards. Okay. I was racking my brain trying to figure out how to solve this one because it didn't give us a standard deviation. I went and looked in the book, and it does. So just need to add that in here because for some reason it wasn't included on this sheet. So the mean throwing distance of a football for Marco, a high school freshman quarterback, is 40 yards with a standard deviation of 2 yards. The team coach tells Marco to adjust his grip to get more distance. The coach records the distances for 20 throws. For the 20 throws, Marco's mean distance was 45 yards. The coach thought the different grip helped Marco throw farther than 40 yards. Conduct a hypothesis test using a preset alpha equals 0.05 and assume the throw distances for footballs are normal. Okay, so we're trying to determine if the grip helped Marco throw the football farther. Now, the mean distance was 45 yards, so that's good, but the question is that statistically significant, right? Or did he just have one really good throw that pulled the mean up higher? So these are what we need to check for. Okay, so first up, let's establish our hypotheses. So our null hypothesis is that his average throwing distance is 40 yards. And the coach thinks that this change in grip helped the distance go greater than 40. Okay, so this is our null and alternative hypothesis. Okay, so the status quo, he's still throwing 40 yards. The alternative, he's throwing more than 40 yards. Okay, so on our graph, right, if that's 40, and somewhere up here is 45, and then the question is that result statistically significant? Is this significant enough to make our claim here? Okay. Now for this one, we need to create our test statistic. So for the test statistic, let me do this up here. So the test statistic, so it tells you to use the t-score for this, do a t-test on this. But since we know, and that's kind of where this different piece of information comes in, since we know what the population standard deviation is, we can actually go ahead and just use a z-score for this. You would use the t-score if you had a sample where we didn't know the population standard deviation. And we'll see an example of that later. But we're going to use the z-score. So we always denote these with a sub-zero next to them. That tells us that it's the test statistic. And we need to compute the z-score. So the formula for computing the z-score would be x bar minus the mean over n over the square root of or excuse me, standard deviation over the square root of n. Right, so that's going to be, so let me just write it here. So that's going to be x bar minus the mean over, sigma over the square root of n. Okay, that's our formula. So in this case, that's going to be 45 minus 40 over 2 over root 20. Okay, and then just kind of plug and chug that, but that's going to give us z naught equals 11.18 approximately. Okay, so we'll hold on to that because we're going to need that. Okay, so we're going to go through the two primary approaches that we're going to use here. So that's the classical approach and the p-value approach. So classical approach, and I should mention you don't have to do both approaches. You only need to run the test once. So if you run the test once, you don't have to run it a second time using a different method, unless you'd like to check and make sure that you get the same result both times. And that's fine, because they will give you the same conclusion. Okay, so once we get our test statistic, we need to then just compare it. So z naught is 11.18. We need to get our critical value. So our critical value, so that's our what we abbreviate CV. That's going to be z sub alpha, so z sub 0.05. And that value we're going to get from the normal distribution. So let me go back to Desmos and show you. So let me get normal distribution back up here. Normal distribution, all right, standard normal, 0, 1. And we want to get the inverse. So we're going to go to inverse CDF. Okay, and for an alpha value of 0.05, we only can plug in the area to the left of that. So we're going to go 0.95 is our area. Okay, and then that gives us our corresponding z-score. So, and I don't, oh yeah, it's just the calculation there. So we can see this is approximately 1.645. So that's approximately 1.645. So if we compare these values, so if we look on the graph here, okay, so this is our mean of 0, right, our standard normal, and we get our z-score of, our z sub alpha at 1.645, and the z naught, our test statistic, is at 11.18, which is so small we can't even see it, but it's going to be way up here, 11.18. Okay, so that's going to be within what we call the critical region. The critical region is everything outside of that alpha value, that critical value. Okay, so that's our critical region. So we have 11.18 is greater than 1.645. It's in the critical region. Okay. So what does that tell us? That tells us that that is highly unusual given the null hypothesis is true. So that allows us to reject the null hypothesis. So our initial conclusion from this is to reject the null hypothesis. Okay. So that's our classical approach. So we just find that test statistic, find the critical value, and then see where they fall on the curve. Okay, now for the other one, so this is our p-value approach. We need to find the p-value. Okay, so a p-value, that's going to be the probability that z is greater than or equal to 11.18. Okay, and then if we go on to our normal curve here, so let me get our normal distribution back up here. Standard normal 0 to 1, and find the cumulative probability above 11.18. And you can see, well, you can see on the curve that you can't even see it anymore, right? But if you look at the value, we're at 2.55 times 10 to the negative 29th power. Okay, so this is an incredibly small number. Right, it's 0 point and then 28 zeros and then 255 approximately. And you can see 11.18 in terms of this curve, that's way out here. So you can see the normal curve is way back over here. Our value is way up here. I have to zoom in really far. Let's see, 11.18. That's going to be right there. And you see on the left-hand side just how small this scale is getting, just for us to be able to see anything under this curve. And Desmos stopped, right? Desmos won't even go that far anymore. That's how incredibly small this area is. Okay, so when we're back here plugging that in, so that's going to be approximately 2.55 times 10 to the negative 29th. So a huge value for us. Okay. We compare this to alpha. So the p-value, that is certainly smaller than alpha, right? And alpha is 0.05, right? 5% level of significance. So since our p-value is so much smaller than alpha, then we reject the null hypothesis. Alright, so, and again, you don't have to do the test twice, right? Just pick one or the other. But we do get the same result out of this. So, what does this tell us? It tells us that the null hypothesis, we can reject it. So we can say there is sufficient evidence to conclude that the different grip helped him throw farther than 40 yards. So we can say there is sufficient evidence to conclude that the different grip helped him throw farther. Okay. All right, so let's look at another one, this time dealing with a proportion. So in 2011, a U.S. Census report determined that 71% of college students are working students. A researcher thinks that this percentage has changed and surveys 110 college students. The researcher reports 91 of the 110 are working students. Is there evidence to support the researcher's claim at the 1% significance level? So with 99% confidence, are we able to support his claim? So let's again start off the bat here with our hypotheses. So let's see, we have our null hypothesis states that 71% of college students work. So that's going to be P equals 0.71. Our alternative hypothesis, researcher claims that this percentage has changed. The researcher didn't say greater than or less than. It could be either. All he said is it's changed. So we're just going to say P not equal to 0.71. And those are going to be our hypotheses to start us off. Now, because we're doing a not equal to, this is actually going to be a two-tailed test. Okay, so this is going to be two-tailed, which means instead of having just an alpha value, you're going to have alpha over 2 down here and alpha over 2 up here. Okay, so this means, so since alpha in this case is 0.01, alpha over 2 is 0.005. So if alpha was 1%, alpha over 2 is 0.5%, right? 0.5%. Okay. And then let's also go ahead and get our p hat value. So that's going to be, in his study, it was 91 out of 110, which is approximately 0.827. So about 82.7% in his study. So that certainly seems higher, right? It seems different than 71%, but we need to determine whether or not that is statistically significant. So let's go ahead and get our test statistic first. So our test statistic is going to be z naught. So this is going to be p hat minus p over standard deviation, which for p values is going to be p times 1 minus p over n, all inside the square root. So might have forgotten that formula, but there it is. So this is going to be 0.827 minus 0.71. Oops. 0.71 over square root 0.71 times 1 minus 0.71, so that's 0.29 over n. His study consisted of 110 people. Okay, so run that through a calculator or through Desmos. We're going to get 2.704 for our test statistic. Okay, so that's our z naught. So we're going to need that to run either of these tests. So again, we'll do classical first. Okay, so we need our z sub alpha over 2. Okay. So z sub, I'm having trouble with my alphas today. Alpha over 2, good enough. So that's z sub 0.005. So if we go into the standard normal curve, and we want to find the inverse norm, so inverse CDF, and then the area to the right of this is going to be 0.005, so the area to the left is 0.995. And that's going to give us approximately 2.576, right, if we want to just round to a few decimal places. So that's approximately 2.576. All right. So if we compare where this is, so this value is 2.576. Our test statistic, z naught, is 2.704 approximately. So 2.704 is actually in the critical region. Right? So we can say, so z naught is greater than z sub alpha over 2. So z naught is in the critical region. So what does that tell us? If it's in the critical region, right, that means it's more unusual to occur if the null is true. So we can reject the null hypothesis. So our classical approach told us that we can reject the null hypothesis. Right? And then for the p-value approach, so the p-value, that's the probability that z is greater than or equal to 2.704. Okay. And this, again, you just go into that z-score, that normal distribution on Desmos, and then your cumulative probability goes from 2.704 up to infinity. This is approximately 0.0034. Okay. And if we compare this, so our p-value, compare that to our alpha over 2 value, that is less than alpha over 2, right, which was 0.005. Okay, so it's slightly less, right? 0.0034 is slightly less than 0.005. So, since our p-value is smaller than alpha, we can reject the null hypothesis. Okay, so we do get the same conclusion each time. So, to answer in context, the researcher was wondering if the percentage or the proportion of working college students had changed, and it looks like, based on our evidence, it has. Okay, so we can conclude, so thus, there is sufficient evidence to support the researcher's claim that the proportion of working college students has changed. So there is enough evidence to support this claim. Again, that's never 100% guarantee. I'll say that after every problem, but it is a strong indicator that that is in fact the case. Okay. So let's look here. We have special cases for hypothesis testing, so we're just going to kind of go through these a little bit quickly. If we have a sample size that is too small, we need to verify that the data come from a population that is normally distributed with no outliers before we can begin testing. So for this example, so according to United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from 5.67 grams. The researcher randomly selects 18 state quarters, weighs them, and obtains the following data. At the alpha equals 0.05 level of significance, is there evidence to conclude that state quarters have a weight different than 5.67 grams? Okay, so what we want to do is we want to take our null hypothesis, and that is that the mean weight is the same, right? That it's 5.67 grams. And the alternative, we're saying that it's different than that, right? Different than 5.76 or 67. Not necessarily greater than or less than, just different. So that's going to be mu not equal to 5.67. However, notice our sample size is only 18. Generally, our rule of thumb is 30. We need 30 for it to be considered significant, to be approximately normal. So we need to determine whether or not this represents a normal distribution. So let's go to Desmos. So luckily I already have this one queued up for us here. So I already created the data set. So if you just type in all of those data points, right, in just a comma separated list within the square brackets, I have all 18 there, and then draw a histogram of the data. And we can see, if I get over to the 5s area here, see what's happening here with this curve. So the histogram, I went ahead and did 0.05 for the bin width. So you can pick whatever you want, but if you make it too big, then that's going to start messing up the shape because now you're getting too much data clumped into a bin or a rectangle. So I'm going to keep that at 0.05. And if you can notice the shape here, so notice that the ones on the outside are a little bit shorter, the ones towards the middle are a bit taller, right? So it may not be perfectly normal, right? Perfectly symmetric, but it looks pretty close, right? It looks pretty close to normal, right? If I do relative, you can see, right? Most of the, you could picture drawing like a bell-shaped curve over this, right? Roughly. Okay, so we are going to go ahead and conclude that it's normal. And that allows us to run our hypothesis test. So in this case, it is a two-tailed test, right? Because it's just not equal to. So we're going to have our alpha over 2 over here and our alpha over 2 on that side. So we're doing it at the alpha equals 0.05 level of significance. So that's 95% confidence. So half of that is 0.025. Okay, so that's our alpha over 2. Now in this case, so before we've been using the z-scores, in this case we are going to need to do a t-test, use the t-score for this, because we don't have a population standard deviation. We're going to get the standard deviation from here, and that's going to allow us to work with this data. So we need to run a t-test here, so we're going to use a t-test. So we need the degrees of freedom. Remember, degrees of freedom is just number of data points minus 1. So that's going to be 18 minus 1, which is 17. Okay, and then we need x bar, so our sample mean and our sample standard deviation s. Those both come, again, from the data set. And you just do those on Desmos. So you would just type in mean of the data set and STDEV, standard deviation of the data set. Just on Desmos, that'll give you the mean is 5.702 and standard deviation is 0.0497 approximately. Okay, so that's kind of our setup, all the information we have just right at the beginning here. So now let's go ahead and get our test statistic. So the test statistic we're going to compute similarly to the z-score. So our test statistic, that's going to be, so t naught this time. That's going to be 5.702, so x bar minus mu, so minus 5.67 over s, so 0.0497 over the square root of n, so over the square root of 18. So we get t naught is approximately 2.732. Right, so again, as per usual, let's hold on to that because we're going to need it in just a minute. So now, let's look at our two approaches. So again, so classical approach here. So we need our critical value. So it's going to be t sub alpha over 2. So that's t sub 0.025. Okay, so let's go on to Desmos and look at this. Because this one does use a t-distribution, so I want to just touch on that. So this one is going to be slightly different, so it's t-dist right there. Enter in the degrees of freedom, which is 17. And now we are finding the t-score that corresponds to this alpha value. So alpha is 0.025, right? Alpha over 2, I should say, is 0.025. So the area to the left of that is 0.975. So that's going to give us approximately 2.1098. Let's try to find a nice number to round at. 2.1098. So that's approximately 2.1098. Okay, so that's our critical value. We already found the test statistic, t naught, right? That's 2.732. And we see that this is clearly greater than the alpha, the t sub alpha over 2 value, right? It's greater than our critical value. So that means it is up here in the critical region, right? In our critical region. So test statistic is in the critical region, which means that it is statistically significant. So we can reject H naught, reject the null hypothesis. Okay. And then let's look at the p-value. Okay, so our p-value, that's going to be the probability that t is greater than or equal to 2.732, given, of course, that the null hypothesis was true. Okay, we can do that. So again, we're going to be using Desmos here, using that t distribution, and just get rid of the inverse function here. So t distribution with 17 degrees of freedom, and we're trying to find that area above 2.732. So that's going to be up here. There it is right there. And that's going to be approximately 0.007. So 0.007. So that's just 0.7%. So very small. So 0.007 is certainly less than alpha over 2, right, which was 0.025. Okay, so it's about a third to a fourth less than that. Okay, so we can, since the p-value is less than alpha, reject H naught. So reject that null hypothesis. So now we can go ahead and make our conclusion. We got the same result both times. So again, you don't have to do both tests, but you can pick which one works best for you, unless a question specifically says you should do one or the other. But generally, it's up to you to decide which one you prefer to do. So we can conclude, so there is sufficient evidence to support the claim that the state quarters have a different weight. Okay, so there is enough evidence for us to make that conclusion. Okay. All right. Then let's look at our last example here for chapter 9. So sometimes if we have a sample size that is too small when we're computing a proportion, when we're running a hypothesis test on a proportion, so if we have this value is less than 10, right, which if it's greater than or equal to 10, we're good because we're approximately normal. But if it's less than 10, we can actually compute the p-value using a binomial probability. So we haven't seen binomial for a couple chapters now, but really it's actually going to simplify our work quite a bit to get that p-value. We're just going to use the binomial distribution instead. So let's read the example. So in 2006, 10.5% of all live births in the United States were to mothers under 20 years of age. A sociologist claims that births to mothers under 20 years of age is decreasing. The sociologist conducts a simple random sample of 34 births and finds that 3 of them were to mothers under 20 years of age. Test the sociologist's claim at the alpha equals 0.01 level of significance. Okay, so we would set up our hypotheses. So the status quo, we're assuming that proportion is 10.5%, so 0.105. The sociologist claims that that proportion is decreasing, so that p is less than 0.105. So there's our hypotheses. Okay. Now the problem here is that if we test, because maybe we say, we say, hey, wait a second, he only tested 34 patients and got 3 of them to be mothers under 20 years of age. That seems like a pretty small sample. Let's check it. So we check to see what happens here if we take 34 times 0.105 times 1 minus 0.105, which is 0.895. And this value is actually about 3.195, which is certainly less than 10. Okay, so we get that this is not approximately normal, so we're going to use a binomial distribution instead. So we're going to use binomial distribution instead. And what this means is that when we're determining our p-value, we're no longer going to look at the proportion anymore. We're just going to look at the count of how many people there were that fit this category. So for our p-value, we're looking at the probability that the number of women who were less than 20 years old was less than or equal to 3. Because that's what they found in the test, that 3 of them were under 20 years of age. So we're looking, what are the odds that that would happen given this population proportion? Okay. So here we're looking at a binomial distribution because it is success or failure, right? Because it's success if they're under 20, failure if they're above 20, given this test. So on Desmos, what we're going to do is we're going to use binomial distribution, and you need to type in the number of trials and the probability of success, right? The rate of success. So we're going to go ahead and type that into Desmos. So get rid of my t distribution here. So let's get the binomial distribution. So that's right here. And it tells you right there it needs the trials and success probability. So 34 trials, success probability of 0.105. Okay, and you can see, if I zoom back out here we are. And if we want to find the cumulative probability, because remember this is discrete, so it's each individual data points. And I want to find the probability that the number of women was less than or equal to 3. So the maximum value is 3. So just including those. And we see that our value we get is approximately 0.5149, right, or 0.515. So we get, this is approximately 0.515. Okay, and now let's compare this to our alpha value. So we get the p-value is 0.515. That is certainly greater than the alpha value, which we had up here, right, is 0.01, which is alpha. And since our p-value is greater, significantly greater than alpha, then we cannot reject the null. Because it's saying, basically, if this null hypothesis is actually true, if that's the actual percentage, we would expect to get 3 or fewer pregnant less than 20 over half the time, right? 51% of the time, which is actually quite likely, right? It's more likely than not that we would get around these numbers. So not only does this not allow us to reject the null, but I would say it even goes towards supporting the null, that percentage is actually fairly accurate. So we say here we do not reject the null hypothesis because we do not have a strong enough case to reject it. Again, it's not saying guaranteed, but we're just saying we don't have enough evidence right now. So we say there is insufficient sufficient evidence to conclude the births to mothers under 20 are decreasing. Okay, so he found some data that suggested, right, that it was going to be under 20, because if you find the p-hat value, his data says that it's about 8.8%. So it is less than 10.5 for his study, but that's not significant enough for us to make a strong conclusion that we can reject the null and actually accept that new value.